Alright, hello everyone. Hopefully the sound will come out okay today. We are going to look at circular motion. And we're going to use our program to invent some new things. Now, we're going to do this in two parts. And we're going to get some ideas out of circular motion, and then we're going to build to them. So in general, we can think of this as like the kinematics of circular motion. And then we're going to move into the dynamics. So in kinematics, in linear motion, we focused on the change in position versus the change in time, and the change in velocity versus the change in time. In circular motion, we're going to have a parallel circular motion. We're going to look at the change in angular displacement for time, and we're going to compare that with the change in angular velocity over time. And so there's a parallel here between linear position and angle. And for angles, we're now going to talk in radians. And so a radian is going to be where I'm going to divide first. And radian really has a calculus and a numerical, and we'll look at it from a unit conversion viewpoint so we can see the power of radians. So if we go back and we think that the circumference of a circle is a thing, 2 pi times the radius. And so let me get a circle here, or semicircular thing, and I will have some radius on it. Sorry, my computer makes that weird noise now and again. I have some radius, and now we will talk in a right-handed system. And a right-handed system has a particular viewpoint. I'm going to try the camera here. If this works out odd, I've not quite set this up for me to be using the camera, but hey, here I am. So in a right-handed system, you're here. My screen's there, you're here. We look at our rotations going this way so that our thumb points up when we rotate. And in a right-handed system, that means the upward thumb is counterclockwise. And so in mathematics and physics, when we talk about rotations, positive rotations are in a counterclockwise direction, or a right-handed system. And this is how we keep track of our signs. We'll be able to make vectors out of rotations. Any component that moves or has a displacement unit, we'll be able to vectorize. But let's look, the circumference is all the way around a circle. And in radian measure, all the way around the circle is 2 pi. We start at 0, we work all the way around, and that's 360 degrees, or 0 to 2 pi for radian measure. And so we have a conversion for radians, and that is 2 pi is equal to 360 degrees. And if I divide that, we can also say that pi in radians is equal to 180 degrees. And the unit is degrees here, but we're going to say radians are unitless. And I'm going to show you why radians are unitless. And that makes them very useful in calculus, because without having a unit, when we do derivatives with them, or when we do some of the stuffs we have to do in physics with them, we don't have to worry about the unit per se. And so there's another formula from geometry where we can talk about arc length. And so if I go all the way around the circle, I get the full circumference. But if I go partially around the circle by some angle theta, that creates what we call the arc length, S. And the formula we have for that is the arc length is equal to theta times the radius. And hey, look what happened here. The circumference is the arc length all the way around times 2 pi. 2 pi happens to be the angle I would make if I went all the way around. So there is a relationship here, and we can actually talk about the angle in terms of radian if I divide r out. It's the arc length over the radius is equal to the angle. But the arc length is going to be measured in units of length, and the radius is going to be measured in units of length. And length over length is unitless. So theta has no units. And so if we use radians, this relationship for our angle, it's technically a unitless measure, which is we're going to find very useful. And so we're going to talk about angular displacements in terms of radians. And so one of the things we have to do is we have to go dig back into our well of unit conversions. Go, I've rotated. Let me make a rotation here. Rotation in green. So I'll start at this angle, and I'll rotate with the same radius. By 45 degrees. And so there's a rotation I'm doing, so this radius sweeps out. If I take some arm and I sweep it from this portion to this portion, well, if my theta is 45 degrees, what is that in radians? Well, I remember that pi equals 180 degrees, so my conversion factor is pi over 180 degrees equals 1. And so if I multiply 45 degrees by 1, I'll get the same thing back, but I'm going to use my special version of 1 here. I'm going to use 1 in this format. And, well, 45 goes into 180 4 times, and that's pi over 4. And so 45 degrees is pi over 4 in radians. And so we'll probably still talk in degrees, and we'll convert it to radians. And we'll move back and forth between 3 ways of measuring an angle. We can talk about a revolution. 1 rev is 2 pi radians. It's all the way around, or 360 degrees. And these are going to be our ways of talking. If I revolve completely once around a circle, I've gone 360 degrees, or 2 pi. If I've gone halfway around a circle, I've made a half of a revolution, I've gone pi, or 180 degrees. And so when we talk in circular motion, our main unit is going to be the radian. Alright, well, let's generalize and talk about complete circles now. And so we'll come back and we'll break down the radian going through. So I'm going to stop this here. I'm going to record this as my radian measure. I'll do this in short little snippets. And then we're going to come back in and we're going to talk about what happens if I'm moving in a circle. And we'll just keep moving in a circle and build out our physics from it. And we'll keep coming back into rotations. And so we'll be talking about things that revolve. Revolution will be the language we use, remembering underneath it that we're tracking some angle of change.